Good morning, everybody. Welcome to a cold Wednesday morning of Chem 1105 with your host, me, Dr. White. Hi, everybody. Well, I have to admit, I made a mistake yesterday. Oh, no, I did. And yesterday, I should have gone through two labs because this week on Tuesday or today, you should be doing labs 9 and 10. I did lab 9. I forgot lab 10. I'll do that after I talk about a few other things. Then we'll go back to molarity and a new chapter. All right, first of all, I'd like to remind everybody I will be postponing, or I did postpone test number 3. Was scheduled for today. It will be a week from today on the 26th. Excuse me. And I will give it right after the end of class. I'll send out a password protect email with the password for the password protected test that you will then be able to download from Blackboard. Also, don't forget, because last week I missed the Wednesday Zoom meeting on 4/12, here are two videos from a former Chem 1105 Zoom meeting class I taught that you should watch. The material in these videos will be on our material you should know for test number 3. Now, speaking about test number 3, today's Wednesday. By the end of the week, Friday, Saturday morning at the latest, I will post and you'll get an email of information about test number 3. But I can tell you it will cover chapter 6, gases, and chapter 5, part 5.5, solutions, including molarity. Next Monday, I will go through the solutions problem set. Make sure you do it before I do. Next Monday, I'll do my world famous review for the next test, which in this case, test number 3. So we're going to be busy next Monday. And don't forget, the 27th, which is next Thursday, a week from tomorrow, will be the deadline for the lab amnesty program. If you haven't handed in a lab that was due earlier in the semester, this is a chance for you to hand it in so you don't get 0 points. Now, yesterday we were talking about molarity. Notice I say we, and really I was, and you were listening, and listening good as seen on test 1 and 2. All right, molarity equals moles of solute per 1,000 milliliters of solution. That's better. Let me get my stylus. So let's do the following. Did it again. I'm so used still writing cursive that I forget many of you never learned it. Generation gap. It's very sad that they don't teach that. I think they're starting to teach that again. All right, let's do the following problem. All right, let's take a look at this. 6 points. How many moles H3PO4, and this is phosphoric acid. And later today, you'll learn what an acid is. How many moles phosphoric acid are in 2.81 times 10 to the third milliliters of a 1.711 capital M H3PO4 solution? So I'm going to ask you first, what are we being asked to find? What are we given? Your turn. Remember, you're trying to find, what are we being asked to find? What are we given? All right, you can hit pause if you need more time. If you're watching this video, what are we being asked to find? How many moles? And I like to use the question mark saying, that's what I'm trying to find. How many moles H3PO4 phosphoric acid, and then you're given 2.81 times 10 to the third, excuse me again, milliliters, and you're also given this 1.711 capital M H3PO4 phosphoric acid. Now, you should remember, capital M means molarity. And molarity is equal to moles solute for 1 liter, but in the lab we use 1,000 milliliters. And as I promised, keeping down with the amount of memorization you have to do in my class, for test 3 important information, you will be given this for molarity. Moles of molarity equals moles of solute per 1,000 milliliters of solution. Guess what I forgot to do? After this problem, we'll do lab 10. I forgot it again. Oi. All right. So the only number we have to work with is this. Next, what units are we trying to get to? Our answer. Well, we figured it out there. And now, how do you figure out what goes on top? First, let's do 2 stages. First of all, what units go on top? What units go underneath that ratio? Your turn. And use your good buddy, your good friend. Time's up. I like my buzzer sound. All right. Whatever we're trying to get to, when you use your good buddy, your good friend, unit analysis, the units go on top of that ratio. Whatever you're trying to get rid of, the units go underneath. And where do we get this ratio of moles of H3PO4 phosphoric acid per milliliter? We look right here. capital M, molarity. And therefore, what does this mean? It means 1.711 moles of phosphoric acid, HP3O4 per 1,000 milliliters. So I can put in here for every 1.711 moles of H3PO4 per 1,000 milliliters. Before I pick up my calculator, actually I'm reaching over to get it. Before I even do that, I'll look and see milliliters divided by milliliters cancel out, because anything divided by itself equals the number 1. And now I look and what's left? Moles of H3PO4, which is what I want. So 2.81 blue double E 3 times 1.711 divided by 1,000. And my calculator gives me this number. And remember, when you're doing a calculation, you should use significant figures, because on test 3, it will say for all calculated answers, please use significant figures. Also say, please use all atomic masses, the 3 significant figures. And how do we do that? When you're multiplying and dividing, the number you get that has the same number of significant figures as the number you're multiplying and dividing that has the fewest significant figures. And all non-zero numbers are significant. So that's 3 significant figures, 4 significant figures. The 1,000 is part of the definition of what molarity is. That's defined. So this is an exact number, which doesn't play a role in significant figures. So which is the lower number, 3 or 4? Hope you all picked 3. So now please round this off to 3 significant figures. Your turn. Time's up. Keep the 4, keep the 8, keep the 0. That's my 3 significant figures. Use the 7 to round off. Is that 4 or less or 7 or higher? And hope we all pick 5, 7 or higher, 5 or higher. I'm looking at the number 7 and it got burned in my brain for a second. And therefore you increase the one in front by 1, because that's 5 or higher. 10 to the 0 is 1. 1 times 4.81 is 4.81. And both of these are moles of H3PO4. And that's how you do it. Now, before I forget, which I just did, we better do lab number 10. Oh, excuse me. Now, if you look, lab number 10, shorthand MOL is molecular models and VSEPR. And notice I have the lab, both as a PDF and a Word doc that you have to do. And this is a handout. And you'll use that and fill it in. Let's take a look at this. But before we do that, note in Chem 1105, the molecular data sheet only do the following molecules for, I guess it's table 2. And you do not have to fill in the nonpolar or polar column in the last chart. Also for this lab, no selfie is needed. Are you going to hold up a piece of paper? No. All right, let's look at the lab. And here's the lab. There's no real write-up. When I say write-up, explanation. We talked about VSEPR in lab in the lecture, but let me direct you to the following. If you go to Wikipedia, did I tell you I used to call it Wikipedia? My students when we were face to face, no, Dr. White, it's Wikipedia. And they finally taught me, which was a good thing. All right, now go to Wikipedia and put in VSEPR theory or just VSEPR, and you'll find this page. VSEPR stands for valence shell electron pair repulsion, and then it's a theory. Essentially, the theory is centered around the fact that electrons repel each other. They don't want to be close to each other in pairs. When you have a pair of electrons, they don't want to be near any other electrons. They're happy. You know electrons could feel things. Yep, you can have happy electrons. But that was lame. But anyways, they try when the pairs to be far apart. And that's where this comes in. And you have to consider both the bonded electrons and the non-bonding electrons. And if you scroll down, they have two really nice charts. And the first chart just shows you a center atom A. And if it has, like here, bent, it has two atoms attached to A, and then one pair of lone electrons, see right up here. And the shape of that will be bent like this. And they have others like trigonoplanar, tetrahedral, and so on. And if you scroll down to the second chart where they have the models, they even give you examples. And look there. And look at the examples. They'll help you out. And what you need to do are a couple things. Some you've already done on test 2. And let's look at those couple of things. Answer all the questions. Now, for question 2, you don't have to explain with examples. For question 2, you do not, I didn't write this up, or I would take that off. All right, question 3, what are valence electrons? You should know that already. Question 4, draw the Lewis dot structure for each of the following atoms. Remember, Lewis dot are valence electrons. And how do you find valence electrons? We have to wait until I open up a periodic table. There it is. And as you see on your screen, the periodic table, the number of valence electrons for an element, you can see written in red by Dr. White, because I found out a couple of years ago, most of you don't know how to read Roman numerals. Why? They stopped teaching that in school too. And notice carbon has 4 valence electrons. You know Roman numerals, IV is 4. So you should know how to do that. And remember, when we're drawing a valence electrons or the Lewis structure, put 1 dot on each side before you double up. That's just for the elements. Now, in this chart right here, you need to draw the Lewis dot structure for these molecules, not all of them, and then write down the shape. Now, I'm going to help you out. I'm going to do the first one. So all of you better get this right. Carbon, 4 valence electrons. Hydrogen, 1 valence electron. Looks like hive. I better make it a number 1. Ooh, beehive. Anyways, carbon's in the center with its 4 valence electrons. Each hydrogen has 1. Says, oh, carbon, you have a valence electron. I have a valence electron. Let's share. And they do. Now, that's the Lewis structure. How do you get, remember, you don't have to do this part. It's not applicable, or I could have written NA. You don't have to do this. All right, but the molecular shape, you do. Well, how do you get that? Well, if you look at carbon, does it have any non-bonding electrons? No. How many bonds does it have? Single bonds. 4. So I can either do this chart or I can come up here to this chart. Where is it? And notice X means it's an atom. A is the center atom. And if you have 4 bonds to a center atom, the structure is tetrahedral. That looks like this. And the CH3, by the way, CH4, not CH3, is methane. And you know this as natural gas. This is what you burn if you have a gas oven or a gas stove. So the shape is tetrahedral. And then I'll let you do the ones that you have to do from this table. You don't have to do all of them. And this is also due next Tuesday. So next Tuesday, you have, hold on, you have 2, not 1, 2 labs to hand in, 20 points. So make sure you hand them in. And don't forget to do lab amnesty. And with that, that's lab 10. I would have forgotten if I just didn't do it again. I already did it once yesterday, once today. Got it done today. Nope, I'm not sweating. It's cool out there. How'd you like our spring and summer now that we're back in winter? Boy, I had to go out this morning. It's cold out there. It's supposed to warm up today, though. But next week's supposed to be cold. All right, let's go back to molarity. If you remember this problem, the question was how many moles phosphoric acid are in a certain amount, milliliters of a certain molar solution. And I showed you how to do this. Let's do the next type of molarity problem you should know how to do. Yep, 10 points. Oops, I don't want that one. All right, the question is, how many grams NaOH? NaOH, I'll teach you next chapter, is a base called sodium hydroxide. And its old name was lye. How I got that, I don't know. But anyways, how many grams NaOH are needed to make 876.1 milliliters of a 2.37 capital M NaOH solution? All right, you know the drill. What are you being asked to find? What are you given? Your turn. Oops, I don't want to do that. All right. Question is, what are you being asked to find? What are you given? Well, I asked how many grams, G is grams, NaOH. What are you given? Well, you need to make 876.1 milliliters of the solution, and you're given this number, 2.37 capital M NaOH. So I look at this and I'm going from milliliters to grams. You can't in one step. This is a problem that needs 2 steps. And if you look at important information, test number 3, which we will, you'll see molarity 2-step problem. Step 1, milliliters to moles. Step 2, moles to grams. And you know how to do that. So let's get to work. You're given something in milliliters. The first step is you'll convert it to moles. Well, the only number we really have to work with is this. So I will. If there was some ratio, what units do you want your answer to be in this first step? Moles, but moles of sodium hydroxide. And now, what units go on top and bottom of that ratio? Your turn. I'll be generous today. I'll give you 15 more seconds to figure out what units go on top and bottom of this ratio. Go, go. Get started. That doesn't sound good either. Looking at the seconds click off. They don't actually click. It's a digital watch or clock, actually. All right. How do you know what units go on top and bottom of this ratio? Use your good buddy, your good friend, unit analysis. I love this thing. I've got 4 others. They don't leave my house because the company's been long out of business. They don't make them that good anymore. Whatever you're trying to get to goes on top of the ratio. whatever you're trying to get rid of goes underneath. So I'm going to write that in. Oh, did it again. It's script. No, it looks the same way, but anyways. So where do we get these numbers? We look up here and say, what does this mean? Ooh, capital M. Molarity equals moles of solute per 1,000 milliliters. In this case, it's, let's go over here because I'm running out of room, 2.37 moles NaOH, sodium hydroxide, per 1,000 milliliters. So I can put 2.37 here and 1,000 milliliters there. And before I pick up my calculator, I see milliliters divided by milliliters cancel out, because anything divided by itself equals the number 1, meaning it's gone. And now I can happily pick up my calculator. $876.1 times 2.37 divided by 1,000. And my calculator gives me this number. And when you do multiplication division, you get the same number of significant figures in your answer as the number you're multiplying and dividing that has the fewest significant figures. So I'll help you out, but you'll have to do this on your own on a test. Oops. 4 significant figures, 3 significant figures. Remember, all non-zero numbers are significant. And this is an exact number because that's part of the definition. So what's the lowest number? 3. Why don't you round this off to 3 significant figures? Time's up. Keep the 2, keep the 0, keep the 7. That's my 3 significant figures. Use the 6 to round off. Is that 4 or less or 5 or higher? You know it's coming. And you were right. It's 5 or higher. So I'm going to drop all this, increase this by 1, and this is equal to 2.08 times 10 to the 0 moles. I keep on one. It's cursive Wednesday. Moles sodium hydroxide. And that's same as saying 2.808 because 10 to the 0 is 1. Are we done? No. We figured out, and I forgot to put here, bad Dr. White, this is what we're trying to solve for. That's what the question mark. So we need 2 steps. We just did step 1, milliliters to moles. What's step 2? Well, in case you forgot, you can look at important information. Test number 3, I say test number 2, test number 3, step 2 is moles to grams. Again, step 2 is moles to grams. So now it's time for step number 2. Moles to grams. Well, we just figured out we have 2.08 moles sodium hydroxide, and we need to find out how many grams sodium hydroxide that is. And it's time to use your good buddy, your good friend, unit analysis. You figure out what goes on top and bottom unit-wise of that ratio. And time's up. If you want, hit the pause button right now if you're watching this video. I'm in pause. Anyways, using unit analysis, your good buddy, your good friend, whatever units you want to get to, go on top of that ratio. Whatever units you want to get to or get rid of, go underneath. Again, whatever units you want to have in your final answer goes on the top of the ratio, and the units you want to get rid of go underneath. And I'll write them in. Oops. Sorry. So we have grams of NaOH, sodium hydroxide, per moles of sodium hydroxide. Where do we get those numbers to fill in that ratio? Well, in case you forgot from test number 2, important information, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights of that compound. Now, sodium hydroxide, you have 1 sodium, Na, right over here, atomic number 11. And test number 3, it will say, please round off all significant figure, please round off all atomic masses, got confused there, the 3 significant figures. And sodium, 22.989 would be 23.0. You have oxygen at 15.999, round that off to 3 significant figures. Yep, you're right, 16.0. And we go all the way over this side of the periodic table. Hydrogen, atomic weight, 1.008. Round that off, 1.01. Oh, lost my train of thought, sorry. All right, so we need sodium, 23.0, oxygen, 16.0, hydrogen, 1.01. Unfortunately, I didn't get a good night's sleep. Shh. That's why I zoned out for a second. Shh. So we need, for every 1 mole of sodium hydroxide, the molecular weight of sodium hydroxide. That's the sum of all atomic weights, 1 sodium, 1 oxygen, 1 hydrogen. We add this up. Remember, when you're adding, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. And that's this way. This has one significant figure to the right of the decimal, one significant figure to the right of the decimal. Ooh, two significant figures to the right of the decimal. What's the lowest number? Excuse me. Hopefully you pick 1. Therefore, you have to round this off to 1 passed to the right of the decimal. Keep the 0, use the 1 to round off. Is that 4 or less? The answer is yes. So the molecular weight of NaOH is this, and 1 mole equals the molecular weight of sodium hydroxide. And now, before I pick up my calculator, got my hand trained. Moles of sodium hydroxide divided by moles of sodium hydroxide cancel out, because anything divided by itself equals the number 1. And I'm left with grams of sodium hydroxide I want. And now I'll pick up my calculator. And put in 2.08 times 40.0. And my calculator gives me this number. And if we look at this, this is 3 significant figures, 3 significant figures. The 1 is the exact number, doesn't play a role in determining significant figures of your answer. And your answer should have the same number of significant figures as the number that has the fewest significant figures. In this case, they're both 3. Oh, look, our calculator gave us 1, 2, 3. And this is our answer. 8.32 times 10 to the first grams of sodium hydroxide. You make a solution of this volume with that many grams of sodium hydroxide, that's what the molarity will be. Now, this is a multi-step calculation. There's 2 philosophies. I follow the philosophy round off at each step, but other people round off at the very end, which I don't like to do for my own calculations. But on my test and final, a problem like this, I will calculate both ways of rounding off. Sometimes numbers are the same, sometimes they're different. If they're different, if you pick either one, you'll get full credit. Now, speaking about credit, for a 10-point answer question, 10 points, if you put down only the number and it's wrong, I'm going to give you 0 points. If you put down the number that's wrong, but you showed your work and it's correct, I'm going to say, oh, you made a math error. Let's assume you added up here instead of 40.01, somehow you got 43.01. And I'd see that and say, oh, math error, I'll take off 1 point, you'll get 9 points, assuming you did the rest right. So it always pays to show your work on those type of problems on my test and final. Trust me, it helps you get a higher score. You make a mistake like that. And with that, we're done with chapter 5, part 5.5. We've covered all the material for test number 3. Monday, I will go through the solutions problem set. Monday, I will do my world famous review for next test, test 3. And by this weekend, I'll post the point breakdown and everything for test 3, how many pages. And with that, and if I look at the clock, this would be a good time to take a break, take about a 5-minute break, and I can get up and stretch. I'll see you in 5. All right, sorry about the delay. I had to find something that I'll be using in a little while. All right, guess what time it is? It's new chapter time. You're going to learn about, I already know, acids and bases. Now, of all the material I'll teach you this semester, this is probably the most useful to you for the rest of your life. So let's get to work. Let's get back to the top of this chapter. Whoop, there we are. So this chapter, chapter 7, is acids and bases. What's an acid or what's a base? Well, it turns out that's not a simple question to answer. And it took chemists a long time to figure out what is really an acid, what is a base. Now, the first to come up with and by the way, click, switches off for this slide, is Arrhenius. And Arrhenius came up with an acid-base theory. An Arrhenius acid is a hydrogen-containing compound that in water produces hydrogen ions, also known as H+. An Arrhenius base is a hydroxide OH- containing compound that in water produces hydroxide ions. Now, example of that would be HCl. When you put it in water, it forms hydronium or hydrogen ions plus chloride ions. This is an acid. And this you don't have to write down yet. And if you have sodium hydroxide in water, this dissociates the sodium cations plus hydroxide anions. Therefore, this is an Arrhenius base. Now, when we talk about acids and bases, and this will be true for something else, you should know the name and structure of the following. Oh, it's subtle time. And you should know the name and structure of some key acids. First one is hydrochloric acid, and that's HCl. Second one, sulfuric acid, H2SO4. Now, sulfuric acid is probably one of the most widely used chemicals in the world. Really? Yep. One of the big uses of sulfuric acid, besides a chemical that helps make other chemicals, is a car battery. And let's go to images. And they don't show, here they show one. If you look inside a car battery, you'll see plates here, but you'll also see a liquid. And that's a solution of sulfuric acid, H2SO4, in water. And all car batteries, regular batteries, not the newer ones for electric cars, that's a different type of battery. But this battery that starts your car, if you have a regular combustion engine, has sulfuric acid in there. Another important acid is nitric acid, HNO3. And nitric acid has many uses, and one of them is to make certain compounds such as dyes. It's used to make with sulfuric acid other compounds such as explosives. Now, the last one, this you don't have to know, but I'll write it down. This is acetic acid. And when you take 4% acetic acid approximately and mix it with approximately 96% water, you get a compound that all of you have in your house, I would assume. And we call that vinegar. Regular clear or white vinegar is essentially acetic acid solution in water, an aqueous acetic acid solution. You should know these key structures. Hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3. Now, let's look at some key bases you should know. First of all, a widely used base is sodium hydroxide, NaOH. The old name, which you don't have to know, is lye. Next, potassium hydroxide, KOH. And that's old name is potash. How did it get a name potash? Well, one theory is, at least I think it is, underneath the pot you boiled your dinner in long ago, you had wood burning. And scientists found in the ashes of the wood potassium hydroxide, potash. Now, another important base, very important, is ammonia, NH3. Ammonia is used to make fertilizer. Ammonia is used to make many products you use in your daily life. I have patents using this, or a derivative used to made from ammonia to make things like fabric softeners and antimicrobial compounds. And it's also used for other things such as explosives. Yep, that's the important part. The last one you should know, the structure of a key base is baking powder, and also baking soda is sodium bicarbonate, NaHCO3. And you should know the structure. Ooh, I forgot to be subtle. Hold on. There, being subtle. And know this. And what do I mean by know this? If I ask on a test, 3 points, give the structure of sodium hydroxide. You should know it's NaOH. If I ask on a test, 3 points, give the structure of NaOH, and NaOH, I did that. NH3, ammonia. You should know how to draw ammonia. The other thing I should, for this chart, if I ask on a test, oops. I ask on a test, 2 points each, maybe even 3, but 2 points each sounds right. Are the following an acid, base, or salt? And if I were to put down this, you should know KOH, potassium hydroxide, is a base. If I were to put down this, sulfuric acid, I gave it away, H2SO4 right here, that's an acid. It says sulfuric acid. And this would be a base, acid. I was looking at this name and not thinking. And let's give one more, sodium chloride. Is that an acid, base, or salt? You put it on your French fries. That's salt. Sodium chloride, table salt. So you should know these structures, their names, and whether they're an acid or base. Now, earlier, just a little while ago, we talked about what's an Arrhenius acid, what's an Arrhenius base. And I said, click, switches off. Why'd you do that? Because the problem with Arrhenius acid base theory is water. You have to do things in water. And a lot of chemistry is not done in water. You know, this stuff, water. So how do you know if you have an acid and base if you're not doing something in water? And that's a major problem. And theories from various chemists afterward to replace the Arrhenius theory had a problem. And the problem is anything in their theory that was an acid or base had to have been an acid or base in the Arrhenius theory. And it turns out two chemists independently, Brønsted and Lowry, came up with an acid-base theory. And why? What was the reason they had to come up with a theory? Because the Arrhenius theory does not explain acids and bases in non-aqueous solutions. This means solvent is not water. In Arrhenius theory, you need water. So let's look at the Brønsted-Lowry theory of acids bases. You know something? Let's do something first. Now, if you look here, let's find, this might be a good place to look. And here's pictures of Brønsted and Lowry, and they independently came up with the same theory at the same time, which is why they have their name associated with this. And they are both physical chemists. And this was back a long time ago now, 100 years ago. Wow, that is. In 1923, Lowry is English, and Brønsted, I believe, is from Denmark, and Danish. Let's look at what is this Brønsted-Lowry theory and base. All right. If it was a dial, I could only put up to 10. I've just put it up to 50. Big hint. Know this. What is a Brønsted-Lowry acid? It's any substance that can donate a proton. A proton is H plus to another substance. And if you notice, I have my favorite color here, red, which I don't use that often in a slide. That means it's really important. You should know a Brønsted-Lowry acid is a proton donor. I don't know where I came up with this years ago. Here, take my proton. I'm a Brønsted-Lowry acid. You should know what is a Brønsted-Lowry acid. If I ask on a test, 3 or 4 points, what's a Brønsted-Lowry acid? It's a proton donor. If I ask on a test, what is a Brønsted-Lowry base? And you should know this. This also, if I was a dial, I could turn to 10. I've just turned it up to 100. I stole that from This Is Spinal Tap, sort of. And a Brønsted-Lowry base is any substance that can accept a proton, proton being H plus. So a Brønsted-Lowry base is a proton acceptor. If I were a Brønsted-Lowry base, I'd say, give me your proton, give me your proton. I want to accept it. And a proton is H plus. So let's review this again. What is a Brønsted-Lowry acid? It's any substance that can accept can donate a proton. I got mixed up. I was on the wrong slide. Let's do that again. Back up. What is a Brønsted-Lowry acid? It's a proton donor. What's a Brønsted-Lowry base? A proton acceptor. How can I show that? Not like that. Wrong button. In chemistry, we use shorthand. HA is shorthand for an acid. When I say acid from now, I'll always be talking about a Brønsted-Lowry acid. And this is real clever. B is a Brønsted-Lowry base. And if you react an acid and base together, this H plus will go to the base because an acid is a proton donor. You lose H plus, this becomes A minus, and the base picks up H plus, and this becomes that. So HA is an acid. Why? Because it donates a proton to B. How can you tell that? Over here. And also here, you lost a proton. It was HA, lose H plus, you have A minus. How do you know B is a base? That's because it accepts a proton. Here it's B, here it's HB. Let's take a look at this in real life. And this is a reaction you can do. I've done it for demonstration. I don't have these chemicals at home. Or, oh wait, maybe we can see this. All right, now, HCl, hydrochloric acid, is an acid. Ammonia, NH3, is a base. Therefore, if I put the two together, this will transfer. Remember, acid, proton donor. It will lose a proton, be the chloride anion. The ammonia will pick up a proton, hydrogen, and a plus sign. So I have 3 + 1, heavy-duty math time. And that's how you know. This accepted a proton, it's a base. The HCl donated a proton, it's an acid. Now let's see if I can find something. I've never looked for this before. So, great moments in Dr. White's lecture time. All right. Let's see how good this is. Trying to find one that's not too long. All right, let's look at this one right here.
We're going to look at an acid-base reaction between HCl gas and ammonia gas. There's still a transfer of a hydrogen ion from the acid HCl to the base ammonia. It will produce ammonium chloride, which is a solid, which we'll see as smoke coming out of the tube. I'm going to add some concentrated aqueous ammonia to one of the flasks.
This is going to be really neat. Check this out.
We're going to add some concentrated hydrochloric acid to the other flask. Most of our studies with acids and bases are going to be in solution, but you do not need to have an aqueous solution to have an acid-base reaction.
What he's doing is that air is pushing the vapor of the ammonia and the hydrochloric acid, and that was forming NH4 plus Cl minus, which is this solid, which you see is that smoke. Let's see that again. This is neat.
Most of our studies with acids and bases, but you do not need to have an aqueous solution to have an acid-base reaction.
What he's doing is the air from the balloon is pushing the vapor together right here in the tube that the white smoke is coming out of. And that was an acid-base reaction. Saw how fast that was. Wow, that was neat. I'm going to have to save this. All right, so let's review again. A Brønsted-Lowry acid is a proton donor. You can see how important it is. How many times have I said that? You should know. Brønsted-Lowry acid is a proton donor. Brønsted-Lowry base is a proton acceptor, and a proton is H+. Now, as I showed you, and you just saw, let's go over to my whiteboard. Here you saw that reaction. Now, I have it written this way, and you form a ionic bond between the NH4 plus and the Cl minus, and this reaction, you actually make this, which as you saw was a solid. S in a bracket means solid. They used this as instead of liquids, gases. You can do the same thing, pouring liquid solutions of hydrochloric together, but it was more dramatic. Who was it? I love that. Now you know I'm a chemist. I'm all excited. Oh, that was great to watch. But anyways, proton donor, base, proton acceptor, and this is what you get in what's called an acid-base reaction. Now, it turns out water, even though the Arrhenius theory had to be replaced because not all reactions are done in water, it's still important solvent to run reactions in. And when you form the hydronium ion, it reacts with water or when you form the hydrogen ion right here, and it reacts with water, it forms the hydronium ion. And there's actually a covalent bond formed. Now, the hydronium ion is an ion because it has a +1 charge. It has an extra, or it's missing an electron or sharing an electron with the hydronium ion. Now, I showed you this reaction already, so I'm going to go to the next slide. Now, in chemistry, there's an important concept called conjugate acid, conjugate base. And this is because a proton transfer occurs. Now, in this class, we don't teach it. These double arrow mean it's in equilibrium. And what that means is the rate this way, how fast it goes, is the same as the way the rate going backwards. Unlike all reactions I've shown you this semester, it can go from left to right, or it can go from right to left. And this is called a conjugate acid pair. Now, what is a conjugate acid? What's a conjugate base? Well, it differs from what an acid and base is. And those are two species that differ from only one proton. Oops. Now, before I taught you about conjugate bases and conjugate pairs, I just had this proton transfer. And I should mention, in a reaction, it doesn't matter which is first, the base or acid. It's no convention. So I could have written this B plus HA. Let's try this again so it looks nicer. That's better. Now, what you now have to know is acid-base reaction are in equilibrium. It can go to the right. Let me do a better double-headed arrow. It's bad drawing day. Sorry. And it can go backwards. That means it can go both ways at the same time. And this is called an acid-base reaction, which are equilibrium reactions, which we won't go into. But let's look at the conjugate pair of this reaction. What's a conjugate pair? It's a molecule that only differs from another molecule by H plus. Now, here's a good hint. Well, for you, look at molecules that only differ by H, hydrogen. Forget about the charge. If we look here, HA on the left, A minus, the only difference is H plus, count the hydrogen. And if we look at the next one, B only differs from HB by H plus, count the hydrogen. Trust me, trust me. Peace. Oh, that's a blast from the past. My past. All right. What do we call the ones on the right? The ones on the left are always either acid or base. I'm going to abbreviate conjugate and conjugate. Now, how do you know what is A minus? You look at when A minus now goes this direction. Let's see how this color. Oh, I don't like that. Let's try another color that I might like. Oop, too big. Well, let's just go with black. When you go from A minus to this direction, this conjugate HA, does A minus accept the proton or donate? Well, A minus has 0 hydrogens, count the hydrogens, it's easier. And it goes to having 1. And it means it's accepted H plus. If you notice the charge is gone, something that accepts a proton is a base. Therefore, A minus is called the conjugate base. Let's now look at HB plus. Is that a conjugate acid or base? And the answer is when you go from HB to B, again, this direction, right to left, does HB plus donate a proton or accept a proton? Donate acid, accept base. And count the hydrogens, it's easier. And goes from H plus to no H plus or hydrogen. And it donated a proton to A minus going this way. Something that donates a proton is an acid, but because it's on the right side of this equilibrium, acid-base reaction, equilibrium, it's a conjugate base. All right, let's do this, 1 point each. For this reaction right here, identify A, B, C, and D as acid, base, conjugate acid, conjugate base. And I give you parts where to write that down. Now, by definition, everything on the left side, left, in case you don't know your right from left, be nice, Dr. White. And this is the right side. Everything in an acid-base reaction on the left side is either acid or base. Everything on the right side is either conjugate acid or conjugate base. So immediately I can do this because I know C and D have to be the conjugates of A and B. And now we'll take the time to look at, if I look at HCl, which one, C or D, differ by only H plus? Well, it's a chlorine, that's got a chlorine, that's got to be it. Therefore, when we go from A to C, does HCl accept a proton or donate a proton? And the answer is it accepts it. It's an acid. Now, going backwards, going from Cl minus to HCl, does the Cl minus accept a proton, a base, or donate a proton, an acid? Well, count the hydrogens, count the hydrogens. No hydrogen, 1 hydrogen, actually, no H plus, 1 H plus. It's accepted a proton. What is a proton acceptor? It's a base, but because the Cl minus C is on the right side, it's a conjugate base. Now let's look at B. B is conjugate, and I made a mistake here. Oops. I'll fix it real quick. B going to D, does it donate a proton being an acid, or does it accept a proton? Count the hydrogens. Here it has 3, here it has 4 plus a plus sign. It accepted a proton. What is a proton acceptor? A base. Now, on the right side, we have to identify D. Is that a conjugate acid or conjugate base? Remember, everything on the right side is a conjugate. And we look at when we go from D to B, does D accept a proton being a base? And it's going to be a conjugate base, or does it donate a proton? It's an acid, it's on the right side, it's a conjugate acid. Count the hydrogens. Went from 4 with a plus charge to 3 no plus charge, so it donated a proton. What's a proton donor? An acid. But it's on the right side. See, it even says it on the screen, right side. Oh, that was bad, sorry. So it's actually a conjugate base. So A is the acid, B is the base, C is the conjugate base, D is the conjugate acid. Now, one thing I should warn you about, students think, well, the first thing on the left side is going to be a base, acid always, second a base. No, I could have put NH3 first. You don't know until you do what I just did. Now, if I look at the clock, it's about time for us to say goodbye, or I say goodbye. All right, remember, test number 3 has been postponed until a week from today, the 26th of April. On Monday, I will be doing the world famous review for test number 3, which will be on Wednesday. Also on Monday, I will go through, because we finished it, the solutions problem set. We've already done the gas problem set. In both of those areas, gases and solutions that are problem sets will be the areas covered on test number 3. And don't forget, we did 2 labs this week that are due next week. Lab 9, which you need a selfie, and lab 10, you don't need a selfie, but read the instructions I have on Blackboard for lab 10, because there's certain parts you don't have to do. Don't forget, tonight I have my office hour from 6 to 7:15 on Zoom. And with that, I'll wish you a great rest of the day. If I don't see you tonight, great rest of the week until Monday. And I'll say, Gang gesund. Goodbye. Bye.